Okay, viewers, welcome to another exciting class with Mr. Simplicity. Let us quickly take a look at this question on limit of a function. It says limit as x tends to 0, 1 minus cos x over x should be simplified. This is basically given as a special limit in some cases. Okay, and if it's given as a special limit, it's usually 0. But in this case, they want us to solve it, which is as good as proving that the answer is 0. So let us see how we will do that. The first approach to this question is to rationalize by the numerator. The numerator says 1 minus cos x. So if I want to rationalize, the conjugate will be 1 plus cos x. So let's see that. So this will become limit as x tends to 0, 1 minus cos x over x times 1 plus cos x over 1 plus cos x. And if you observe, remember anytime you rationalize, you always have difference of 2 square at some point. So if we rationalize here, we have to consider the difference of 2 square, which means it's going to be 1 square minus cos x all square. So this will be equal to limit as x tends to 0, 1 square minus cos x squared all over, multiply the denominator, you have x bracket 1 plus cos x. So when we say cos x squared, it's the same thing as cos square x. It means that what we have now is limit as x tends to 0, 1 minus cos square x all over x times 1 plus cos x. You see? So the first challenge we are supposed to face in this question is that we need the knowledge of trigonometry. The first basic identity in trigonometry says that sine square theta plus cos square theta is 1. And from that arrangement, sine square theta plus cos square theta is 1. If I make sine square theta subject of the formula, I'm going to have sine square theta equals to 1 minus cos square theta. See? And if you observe what we have in the numerator, 1 minus cos square x relates to 1 minus cos square theta, which means I can replace this guy with sine square theta. Similarly, I can replace this guy with sine square x. So all I just need to do is to record that identity and then replace this guy with sine square x. So let's recall that sine square x can replace 1 minus cos square x from what we just proved, from what we have proven here. Okay, so when I will rewrite this again, it becomes limit as x tends to 0, sine square x over x bracket 1 plus cos x. So this is what we have at this point. So the next step, sine square x is the same thing as sine x times sine x, which means I can break this down to become limit as x tends to 0. I have sine x times sine x all over x bracket 1 plus cos x. And according to the rule of limits, this is the same thing as limit as x tends to 0. Sine x over x is a special limit, so that can be separated. But sine x cannot stand alone, but I can make sine x a special limit. Okay, we explained that anytime we see sine x, we can use whatever the sign is carrying, which is x in this case, to multiply it and divide it. Okay, so if I do that, I'm going to have x sine x over x all over 1 plus cos x. So now we can record the special limits to replace them in this at this stage. Recall limit as x tends to 0, sine x over x is 1. Also, limit as x tends to 0 cos x is 1. So that means I can just say everything now is equal to 1 times x did not cancel out. Take note. So since it did not cancel out, it has a value from the limit. X is 0. So it will be times 0. Then everything here is the special limit. That's 1. All over 1 plus 1. Special limit. Because x is 1. So what is left now is 0 over 2. Because 1 times 0 times 1 is 0. 1 plus 1 is 2. And 0 divided by anything is 0. So this is the answer to this problem.